At this moment on this chapter, you should be able to first know how to integrate the inverse tangent, and then you've learned an array of tools to integrate more complex functions. We use the change of variable, and you learn integration by parts. By now, you should have practice enough with each one of these methods that I've taught, and you should know how to make the operations very easily. Your trouble now should be only which method to use in which situation, particularly if the question in the exam doesn't tell you what method to use, which happens very often. Okay, so the idea is that you combine your experience, the one that you have right now, with all the questions that you've solved. And to help you organize the ideas, there is this table that is not extensive. It doesn't fit all different situations, but at least it gives you a hand on this process. Okay, so this is the general expression, a situation in which you have a function where you can spot a chunk of it, where you can spot two chunks that contain one with the original function and the other chunk with its derivative, okay, in which you just perform the change of variable in the original function. Okay, this was the first lesson that we talked about integration. A particular case of this happens with fractions, in which you have in the denominator a function and in the numerator a version, a very close version of the derivative of that function, okay? In which case you just transform by simply multiplying or dividing by a number the numerator to get what you need, and then you use a change of variable on the denominator, okay? For other polynomial functions, this is not supposed to be functions, this is supposed to be fractions, okay? You can use partial fractions. In other words, break it down into simpler functions that then eventually will fall into this situation. Then you have the standard result. You should always be aware of it. If you have something like this or something that can be easily transformed into this, don't forget what this is. This is the, if you integrate this, you're going to have the tan negative 1 of x. Now, I didn't mention this in the previous lessons, but I'll do that now. Imagine that you have a function that contains odd powers of sine or cosine. What do you do there? Well, you can write these as a product of lower powers and then use this identity. Eventually, you will end up with something that can be put into this category. So, for example, sine cube of x, you can write this as sine of x times sine square of x, and then the sine square of x can be transformed into 1 minus cosine square of x. Okay, something along those lines. What if you have even powers of sine or cosine? For example, sine square or cosine square of x. You can also use, it will all depend on the situation, but you can also use a double angle formula. You may have forgotten this because this was taught quite a while ago, but here you have it. The double angle formula, particular for the cosine, involves cosine square and sine square of the angle. So you can break this down and turn it into cosine of 2 times that angle, which will make the expression simpler. What if you have other products that cannot be integrated using these methods? They are usually in the form, I mentioned this before, they are usually in the form simple polynomial times simple exponential or simple polynomial times simple trigonometric function. Situations that don't fit into this, by the way. Well, in that case, you use integration by parts.